Good evening, kids. Today's class we are going to discuss the thermal properties in one shot. Here we'll be discussing about the thermal expansion of solids, liquids. Then we'll go for the calorimetry. Then we'll take the thermal conduction and thermal radiation. So all these ideas and convection. So all these particular 6 topics we'll be discussing. We'll discuss some briefly the concepts and also the basic formulas and different ideas and what strategy we should use for exam. This is a basic thing. So you have to again how to utilize this one shot. Watch the video clearly. It may be around, it will come around 2 hours. Learn all the important concepts and ideas which I'll be explaining. This is the very important part. You have to understand things. Then remember all the concepts and all the formulas. Rewatch it 2, 3, 4 times. When you watch it, no, you'll get an exact picture of what is the meaning of them. Then solve PYQ. Those who are preferring for mains, solve PYQ. Those who are preferring for advanced, don't solve PYQ. Solve different types of numericals around per chapter. So this complete thermal properties of matter, around 50 or 60 will come. Different ideas, solve them, revise them. Definitely you can see the benefit in exam. Okay, fine. Next question comes like, sir, how to, sir, we will, though we are watching it, still we are forgetting. Then rewatch it. See, it's like a movie. Now you watch it, remember it. You're forgetting, again watch it, again you start remembering. So by learning, by repetition only, things you can remember. So how to remember things? By reading again and again. There's no other choice. Though you understand, you'll forget. So repeat many number of times, you'll start remembering. Fine, little bit difficult. All these things are difficult, but there's no choice for you. This is easiest approach. Read many number of times, things will become easier. Nowadays you have technology, so instead of reading that you can watch and learn. Make utilize of all these things. You just watch it 3, 4, 5 times. No, slowly you'll start understanding things. In this way you can strengthen your weak topics. Okay, kids. Okay, now how to plan? What are all topics are there? How to plan them? Next we have the first one, thermal properties of matter in one shot. The first we have the thermal expansion of solids. So first we'll define quotient of linear area and volume expansion, then variation of density with the temperature. They're all formulas. Then we'll explore some ideas, thermal expansion of disk with hole, sphere with cavity, the basic definition. Then time loss, time gain, simple pendulum, effect of temperature on the simple pendulum. Then thermal expansion for rotating objects, how it will influence. Then thermal expansion of rods with springs, thermal expansion of scales, thermal stress and strain, and application problems. These things we'll discuss in the thermal expansion of solids. Then thermal expansion of liquids, apparent and real expansion. Just statical, one small formulas are there. Then calorimetry. What do you mean by specific heat capacity, water equivalent of calorimeter, latent heat of heat, change of state, when ice and steam added to calorimetry problems, then triple point of water. These are some conceptual one. Then in thermal conduction, we'll discuss about the coefficient of thermal conduction, heat current, thermal resistance, series parallel, then thermal resistance of different shaped objects, growth of ice layer in a lake, and a rod connected across hot and cold bodies, melting of ice, all those application problems. Then come for thermal radiation. This is a simple conceptual topic. Cooling and warming of bodies due to radiation, Kirchhoff's law and perfect black body radiation, then emissive and absorptive power, Stephen's law, Newton's laws of cooling, Wien's displacement law, and the convection. So all these things we'll discuss in the thermal radiation. So here there are all topics. I'll cover it within 2 hours. I'll wind up everything, all the concepts, all these concepts, then formulas, then the ideas involved, different ideas, not just mere formulas. You're going to learn concept with formulas. So be alert, watch it carefully and learn things. Then remember formulas, solve PYQ. There's a strategy what you have to follow. Okay, fine. So we'll begin like this. I'll start with the thermal expansion of solids. We'll start with the thermal expansion of solids. There's a first, what I mean by thermal expansion? There's a body, the distance between the atoms. So what is this? There's everything is some structure. So we can treat like this. Everything is one body here. So here I'll increase the temperature. Then the body will start expanding. Now, what is the body? The body will expand like this. What will happen to distance between atoms? It starts increasing. Similarly, when I supply heat, it starts expanding here. So this was the basic idea of the thermal expansion. Initially, the distance between atoms is say some x1. Now the same distance between atoms will increase. The distance between any two atoms will increase. You can check it here. Definitely this will be R2, this will be R1. So in thermal expansion, what actually happens? The distance between the atoms will increase, or the distance between any 2 points on a body will increase. This is a basic idea. So what is the condition for this? Now the distance between any 2 atoms, when you supply heat to a body, the distance between any 2 atoms will increase here. Why do that happens here? So suppose say like at higher temperature, the atom here starts vibrating. As it vibrates, then here because of this potential energy versus interatomic distance curve, if you look at the expansion this one, so suppose say this is x1, call x2. What is the net displacement of atom about mean position will be towards right. This is a main cause for thermal expansion of the solid because of asymmetric curve. There's a so when you supply heat, this will start expanding. Also, this will start oscillating. But the oscillations about mean position are such that it will have more displacement towards right than left. So therefore, there is a net displacement of like atoms about their mean position. So that will be towards right. So this is the main cause for thermal expansion. There's one basic conceptual thing which you have to remember. Right? Distance between, what is the basic condition? Distance between any 2 points will increase. So this is a basic condition for the thermal expansion. There is a rod of length L. Its initial temperature T1 degrees Celsius. I'll increase the temperature. So by supplying this heat, we are heating up this rod. The rod will undergo thermal expansion. Then quotient of linear expansion, it is defined as alpha equal to change in length per unit rise in temperature. This is a basic definition. The unit for this will be per degree Celsius. So what is delta L equal to L alpha delta T? What is the new length? L dash minus L equal to L alpha delta T. The new length will be L into 1 plus alpha delta T. Then suppose say if it is having a length L1 with respect to temperature T1, then having length L2 with respect to temperature T2. L0 is the length at 0 degrees Celsius. Then here we can write this L0 will divide these two, L2 by L1, 1 plus alpha T2, 1 plus alpha T1, L2 plus alpha T1 L2 equal to L1 plus alpha T2 L1. Okay, fine. So now we can express in terms of this. L2 minus L1 equal to alpha T2 L1 minus T1 L2, or L2 equal to L1 1 plus alpha. I have to simplify for L2 no. So there's a one equation you remember. Here let me write it here. This will become 1 plus alpha T2 1 plus alpha T1 minus 1. And there are some problems we'll be using this method also. This, if I simplify it, 1 minus alpha T1. L1 1 plus alpha T2 minus T1. Alpha square will be negligible because alpha will be very small. So there is a one formula. With respect to 0 degrees Celsius, you can use this one. With respect to some T1 degrees Celsius, you are comparing, this should be the formula. Okay, fine. This will be this condition, try to remember here. Next again, coefficient of area expansion. We'll supply it. Earlier this having area A. Now this will become area A dash. Then quotient of area expansion beta equal to delta A by A into delta T. Again A dash into A equal to 1 plus beta delta T. Then what is the beta? Beta should be equal to 2 alpha. This is a basic condition. Coefficient of superficial expansion or area expansion. This is a temperature T1 degrees Celsius. This temperature T2 degrees Celsius. Similarly, if three-dimensional object is there, I'll supply it. This having volume V0, final volume V, initial temperature T1, final temperature T2 degrees Celsius. Then coefficient of volume expansion we can define as alpha equal to delta V by V delta T. So delta V equal to V alpha delta T, V minus V0, or say V dash, will write it better. Final volume V dash minus V equal to V alpha delta T, or V dash equal to V into gamma. It is symbol gamma. So this will become gamma delta T. Coefficient of volume expansion of the object. Similarly, volume, we can write it in the same way. Gamma T2 minus T1, where gamma will be equal to 3 alpha for isotropic substance, and beta equal to 2 alpha. Isotropic means it will exhibit same property in all direction. It will equally expand in all direction. Variation of density with temperature. As we know, the volume will increase. V0 plus alpha gamma delta T. And mass of the substance should not change. Mass equal to density into volume. So therefore, this V, what we can write here? V I can write as m by rho. V0 as m by rho naught, 1 plus gamma delta T. So where rho equal to rho naught 1 plus gamma delta. So the density of substance will decrease, or we can write it as rho naught 1 minus gamma delta by binomial expansion. So as we increase the temperature, the density of substance will decrease. And there is one condition to remember. Volume of substance will increase, density will decrease. Rho will be less than rho naught. V will be greater than V naught. We'll discuss the isotropic expansion. This is at temperature T1 degrees Celsius. This temperature T2 degrees Celsius. These are axes X, Y, Z. As applied, the temperature of object will increase. It will expand equally in all directions. The substance will expand equally in all directions. Alpha X equal to alpha Y equal to alpha Z. This is what happens in the thermal expansion of solids, isotropic substance. It will have same property in all directions. Similarly, this was the length of the object. It's a cubical object. What was the temperature? Temperature of this, let it be initially T1 degrees Celsius. I'll supply heat. The temperature will become T2 degrees Celsius. Then the substance will have different length. Lx, Lz, Ly. Where here what we write here, L dash equal to L into 1 plus alpha delta t. Here it's not like that. Lx equal to L into 1 plus alpha x delta t. Ly equal to L into 1 plus alpha y delta t. Lz equal to L into 1 plus alpha z delta t. Where alpha x not equal to alpha y, not equal to alpha z. And what about beta? Beta you should write like this. Alpha x plus alpha y. What about gamma? Gamma you should write alpha x. I'll write it here. Gamma you should write it as alpha x plus alpha y plus alpha z. And isotropic substance. Yeah, part of a syllabus. All the substance what is we discuss are related to isotropic only. If it is not an isotropic, I'll mention. If not an isotropic, I'll mention it. Otherwise, we should assume everything as isotropic substance only. Okay, fine. Everything we should assume it to be an isotropic substance only. If it is not an isotropic, I'll mention it. Otherwise, we should assume it this one only. Here, what is beta? Beta equal to 2 alpha. What about gamma? 3 alpha. Okay. Next we have the desert disk. With all, I'll increase the temperature. The disk will expand. The hole also will expand. What will happen to the dimensions of hole? It will also increase. Then all quantities will increase. A dash, so first disk R dash equal to R into 1 plus alpha delta t. What about A dash? A equal to 1 plus alpha delta t. B dash, B into 1 plus alpha delta t. The distance between any 2 points should increase. The hole also will expand. The distance between any 2 points has to increase. This is one general idea. So here what we have done, we have increased the temperature. How to increase the temperature? Just supplying heat. By supplying heat, what will happen? The temperature will increase and all the points on the disk will expand. Even the hole also will expand. So what will happen to the width of the hole? The width of the hole also is what the L. The dimensions, it will become L dash. Fine. And if this is H, this will become H dash. What is H dash? Equal to H into 1 plus alpha delta t. And there's one basic idea, try to remember it. Very, very useful for you. Effect of the temperature on the length of the pendulum. So here we are considering a metal stringer. This will be made up of metal wire. Will have quotient of linear expansion alpha. This pendulum is exact at theta degrees Celsius, having a length L. The time period of this is given by 2 pi L by G. As I increase the temperature, theta 1 greater than theta, then it will expand, the length will increase. Proportionally, the time period of pendulum will increase. The time will be lost here. Then similarly, I'll decrease the temperature. What is the temperature? Theta 2 less than theta. Then the length of pendulum will decrease. Then the time period will decrease. Here, the time period T1 will be greater than T. Here, time period T2 will be less than T. Then the time will be gained here. Then the interval of time that is lost or gained, the formula is alpha, change in temperature, or an interval of time. This can be 1 day, 1 hour, 1 second, or 1 minute, or what interval of time? Time interval over which time is gained or lost. This can be in 1 day. 1 day, how much of time lost? That 1 day you have to substitute the capital T. Or in 1 hour, how much of time lost? That you have to substitute here. Alpha, change in temperature. There's a 2, the integer 2. So time interval, how many seconds are lost or gained? That formula based, which you have to remember. See here, as the time period increases, time will be lost. time period decreases, the time will be gained here. So now you select as temperature increases. As the temperature increases, length of the pendulum increases, time period increases, time period will be lost here. So a simple thing you remember, time period increases, time will be lost, time period decreases, time will be gained. So then this can be mixed with gravity also. On the surface of the earth, next I have the simple pendulum. It is going to lose some time on the surface of the earth. To make it exact, at what height we should shift here. Then, so what is the basic formula? So here, it has lost time. So then at this particular T1 equal to 2 pi root of L by G dash. We know G dash equal to G into 1 minus H by 2R. This is 1 minus two H by R. Okay, at a height, H equal to, okay, there's a for H very much less than R. There's a formula. Then as you move up, then height will increase. Definitely the G will decrease. The effective G dash will decrease. Then the time period what will happen? Will increase here. The time period will increase here. So time is lost. So so here we'll do one thing. It is gaining time. It has gained time. To make it exact what happen, it has to taken to certain height here. These are some questions are there. So the pendulum is what will happen is very fast. If you move it to certain height, it will become exact. At what height it should be. So how much of time it has lost, how much of time it has gained here, that much what happen, it has to, we have to make it loose. So therefore as you move up, G dash will decrease, the time period will increase. So what all the time it has gained here, it can be lost by rising it to certain height here. Okay, fine. So this will be delta T is equal to alpha delta theta T by 2. So this is a time gained. How much of time it will gain, that much of time what happen, it has to be lost using this one. Okay, clear? Further I'll explain this concept. So how much of T dash, the time gained, so this should become equal to T1 into 1 plus H by R. Solving this one. So therefore this T dash minus T1 should be equal to T1 H by R. Okay, I'll write only T. So this will be T. So what time it has lost here, what time it has gained here, that much it should be lost at height. So I'll equate these two. There's a time gain, there's a time loss. When it can be made exact? When alpha delta theta T by 2 equal to T H by R. T will get cancelled out. So H equal to 2 alpha delta T by 2. What is delta T? Delta T will come from here. The time gained. Like this, the H alpha will be related here. And there is one formula, try to remember. As you move to certain height, this will be the time lost. What is the conclusion? As the pendulum is shifted above the surface of the earth, time is lost. Okay, with this here it is having T. To make it exact, you have to shift to height H. That height H is given by this particular formula. As pendulum is shifted up above the surface, time is lost. No, thermal expansion of rotating disk. I'll increase the temperature. Earlier T1 degrees Celsius. Now T2, where T2 greater than T1. As we increase the temperature, will there be any effect on the kinetic energy, angular momentum, and angular speed? Now first we'll talk about the moment of inertia. I equal to mr square by 2. So di by I equal to m will be constant, 2 will be constant. 2 into dr by r. What is dr equal to? R into alpha delta t. So di is equal to, this will be 2I, dr by r will be alpha delta t, or dt will write it. Yes, definitely the moment of inertia will increase. The new moment of inertia, I dash minus I equal to 2I alpha dt. So where I dash equal to I into 1 plus 2 alpha dt. Moment of inertia will increase as we supply heat. Actually what we are supplying heat here, we are supplying heat. So on supplying of heat, there won't be any net torque acting. The net torque acting on system will be 0. So definitely what will happen to the angular momentum has to be conserved. So the net angular momentum of system is equal to I into omega. Delta L, as there is no net torque, and net torque is 0. So this will be I delta omega plus delta I into omega. So therefore delta omega equal to minus of delta I by I. Delta I change in angular momentum is equal to 2I alpha delta theta by I into omega. I get cancels, minus 2 alpha omega delta t. So what will happen to angular momentum? Angular velocity will decrease. Okay, fine. So the omega dash less than omega. It will have effect on the rotating objects also. Then the kinetic energy directly, what we can write here, L square by 2 omega. There will be also the change in kinetic energy of the system. K dash equal to angular momentum L will be as it is. So K dash will be greater than K. So the kinetic energy of system has to increase. So whatever we supply it, that only what a part of it will be converted into rise in kinetic energy. Omega dash less than omega, K dash will be K. So the rotating objects also, there will be change in angular speed. If your temperature increases, omega decreases. Temperature decreases, omega will increase. There's a condition try to remember. Next we have the thermal expansion of this particular block with the springs. So initial temperature, let it be T1 degrees Celsius. Is having length L, let alpha be the coefficient of linear expansion. There is an object which will undergo thermal expansion. Let alpha be the coefficient of linear expansion. So as I increase the temperature, the block will expand. Then definitely the springs will undergo compression. There's a thermal expansion. So as we increase the temperature, it will increase. So what is L dash? L dash will be equal to L into 1 plus alpha delta t. How much the rod has increased? L dash minus L. This should be equal to x1 plus x2. Why x1 plus x2? Elongation of the rod. x1 plus x2 is increase in length of the rod. Then this is in equilibrium. The spring is compressed. So here a spring force will be acting. How much of spring force here? 3kx2. How much of spring force here? kx1. At equilibrium, kx1 equal to 3x2 or x1 equal to 3x2. Substituting this, x1 equal to 3x2 and L dash equal to L dash minus L should be equal to L alpha delta t equal to 4x2. Like this. We can calculate the compression in both the springs. And how much x1 will be equal to 3L alpha delta t by 4. Okay, fine. So these are some small ideas are very important. Here we have supplied heat to this. And because of the temperature got increased. Both the springs will not have same compression. They'll have different compression. Next we have this object whose length is L naught. Now I'll increase the this scale, which will read exactly 8 centimeter. You can see here this object. I'll increase the temperature. This particular is having quotient of linear expansion alpha. Then definitely the scale will expand. Then the reading of the scale will be, now length of the object will be how much it is. Earlier the length of the object at T1 degree Celsius, it is 8 centimeter. Now the same length of object will be 7.5 centimeter. There is an error. Actually, what is actual length? This actual length. This is the error in reading. So the scale will read less. Okay, fine. So this particular condition is very important. So if object will not expand, only the scale will expand. Then if you rise the temperature, the scale will read less. Similarly, we'll go for the fall in temperature. Now we'll start with this one. I will this at T1 degree Celsius. Again the same conditions. This at T1 degree Celsius. This will be T2 where T2 less than T1. We are decreasing temperature. The scale, the length of the object, how much it was? 8 centimeter. The scale will contract here. Previously the scale was scale expands. Your scale will contract. Then or the reading of this will be 8.5 centimeter. The length of the object is as it is. The reading of scale will be now 8.5 centimeter. Now the scale will read more. Small ideas like this, try to remember. Sir, if both scale as well as object are there, both will expand, what conditions will come? That will. If both the rod and the scale which is used, if they are expand, then the formula should be like this: measured value at final temperature equal to measured value of the rod at initial temperature 1 plus alpha s minus alpha c T2 minus T1. So based on this, what happened? We can get this one. So here, which will be greater? Suppose alpha is greater than, if the steel expands more than the copper. If the steel expands more than the copper, then the measured value will be equal to measured value at T1. Okay, this is at, okay, this one. And the small correction here. Measured value of rod at T2 degrees Celsius, then measured value of the rod at T1 degrees Celsius, 1 plus alpha s minus alpha c. Based on like which one will be greater, we can get the condition here. And the other one may not be very important. Trying to remember this. Just a small idea. More than this not needed. There's a rod having quotient of linear expansion alpha, and the length is given by length of the rod is how much? Is equal to L. And area of cross section. This is at T1 degrees Celsius. I'll increase the temperature. Definitely the rod will expand. This will be extra length L. Now no stress here. Now also no stress. Why no stress? Because when the rod is at its natural length, there won't be stress. What is the delta L is equal to? Delta L equal to L alpha delta theta. There's a change in length. Okay, agreed. Now I'll increase the temperature. Theta 2 greater than theta 1. Then what we notice here is like the rod is compressed. Here rod at its natural length. Now the rod is compressed. How much it is compressed? By amount delta L. So now this will be stressed. How much it is compressed by delta L? Because at theta 2 degrees Celsius, what will be the length of the rod? L plus delta L by 2. How much it is? Still it is L only. So what is the length of the rod? The length of the rod is still, it is L only. So therefore the rod is compressed here. How much compressed? By delta L. Then Young's modulus equal to stress by strain. Stress will be F by A. What do you mean by strain? Delta L by L. So F by A, delta L by L will be alpha delta theta. F equal to YA alpha delta theta. This will be the force. So a force will be exerted by whom? By the rod on the wall. By the rod on the wall. By the wall on the rod. Okay, there's a force. There's a force exerted by the rod on the wall, by the wall on the rod. Okay, fine. So this called like a thermal stress, thermal strain. So what is the thermal stress? Thermal stress should be equal to Y alpha delta theta. This is called like a thermal stress. How much of energy stored in it? Sigma square by 2y into A into L. Sigma is how much? Y alpha delta theta whole square 2y A into L. Y alpha square delta theta square AL by 2. Okay, there's a energy stored, potential energy stored in rod. There's a force exerted by the rod on the wall. A simple topic, very, very useful. At many places they can ask you. There's a shift in the junction. There'll be, you can see the shift in the junction here. We have to calculate this particular shift in the junction. So as I increase the temperature, both the rods will expand. Both the rods will expand. So what about this rod? Is having expansion and thermal compression. What about this rod? Is having thermal expansion, compression. Okay, this. So now the new length will take about the new length. The new length of this will be L1 dash. Let this be L2 dash. L1 dash, L2 dash. What will be the total length of the rod? L1 plus L2. Should be equal to L1 dash plus L2 dash. Because these are the rigid walls, I'll increase the temperature. Both the rods will expand. Both the rods will expand here. Now, what is L1 dash? L1 dash should be equal to, we should write like this here. We'll write separately first. What is L1 dash equal to? L1, due to thermal expansion and there will be compression. Why do this compression? Because this rod, actually the rod wants to expand, but this green color rod will compress it, no? Will not permit it to freely expand. This is a condition. So what is a, due to thermal expansion will be L1 alpha 1 delta theta. What about the compression? We define the formula like this now. Y equal to F by A delta L by L, FL by AY. So this will become F1 L1 AY1. Similarly, same thing with L2 dash. The rod wants to expand. Due to thermal expansion, it will expand. But the other rod has compressed it. This is due to rise in temperature, the length will increase. Due to compressive force, due to mechanical force, the length will decrease here. Due to thermal expansion, L2 alpha 2 delta theta. This will become F L2 AY2. Substituting these things and solving will get the required answer. Just remember ideas. F1, this is F, only F. So, sir, can you show what is F? F is like this. What is F? This rod, green color rod, will compress it. What is this F? Force exerted by green color rod on yellow color rod. What about this F? Force exerted by the yellow color rod on the green color rod. So the wall and the yellow color rod will try to mechanical compression. This is what mechanical compression. This is a thermal elongation. Similarly, thermal elongation, mechanical compression. This green color rod and the wall will try to decrease the length. So this will become L1 AY1 plus L2 L2 alpha 2 delta theta FL2 AY2. Solving will get F, then substitute that F will get the length. And what is the shift in the junction? L1 dash L1. And you can calculate thermal stress in each rod. Same stress it will be there. If the two rods are welded, I'll increase the temperature. Rod 1 will expand, rod 2 will expand. If they are not welded, rod 1 will be at its natural length and no stress here. And here also no stress. So they are at natural length. But here if they are welded, the blue color rod will expand more than yellow color rod. And because of this, what will happen? The blue color rod will be compressed and yellow color rod will be elongated. They'll attain one common length here. You can see here. At theta 2 degrees Celsius, the length of the yellow color rod should be equal to say some length here. But it is elongated more because of this like a mechanical force. Similarly, the blue color rod should have this much of final length, but it's being compressed because of this mechanical force. So at equilibrium, this mechanical force will be equal. Then what is the force account tank molar Y1A? The change in length, delta L minus L1. What is delta L1? Elongation, thermal elongation. So what is the net elongation will be? This will be, the stress will be delta L minus delta L1. Here delta L2 minus delta L. Solving what is delta L1? Thermal elongation, delta L2 thermal elongation second rod. Solving will get the elongation of both the rods. There's a basic idea which you have to remember. Very important, can be asked. Two rods connected end to end, two rods welded. There's a basic condition. We have this metal ball. It's having a theta 1 degree Celsius, having radius R. Let B be the bulk modulus. I'll increase the temperature, it will expand. Then there won't be any stress. But if I don't permit it to expand, then shall we say it is a stressed, or better you say like a compressed. Whenever a solid object not at its natural length will be stressed here. So what is the change in volume? The change in volume should be equal to V gamma delta theta. So that's the initial volume. Then according to the bulk modulus, dP by delta V by V. So dP is equal to D, this will be gamma delta T. So how much of volume stress? B gamma delta T. This is called like a volume stress. So this much is what the volume stress. So here it is being compressed. So okay, what are these arrows? These arrows about like a, it is being compressed. Some agent, I'm not showing it, is being compressed, not permitted to expand. Therefore, it is being stressed here. This will be the volume stress set up in this rod at theta 2 degrees Celsius. This is a bimetallic, two brass in this one. At one end it will be connected. At one end it will be rigidly fixed here. I'll take some other color. No, what I do is like I will there's a rod. I will increase the temperature. Then if I increase temperature, then this will be alpha B alpha S. What is the condition? Alpha B greater than alpha S. If you increase the temperature, it will bend like this. If you decrease temperature, it will be like this. Then what about this radius of curvature? This radius of curvature is directly proportional. Earlier T1 degree Celsius, T2 degree Celsius. This is T3, where T2 greater than T1. T3 less than T1. This radius of curvature, it depends on what all, like the thickness D, then alpha and change in temperature. So greater the rise in temperature, more curvature it will be. It will bend more. Or greater the rise in temperature, less will be the radius of curvature. Or it will bend more. Then greater the difference between alpha and beta, then radius of curvature will be more. Then radius of curvature means it will bend less. Okay, there's one basic condition. Directly, already they asked plenty of times, so remember it, this particular formula. The radius of curvature. So here it will be, the radius of curvature will be formed. The center of curvature for this part will be here. If alpha is greater than alpha beta, if you increase temperature, it will bend like this. There's a bimetallic strip, small idea. At one end both will be clamped, other end free, and they'll be riveted, they'll be welded. If you increase temperature, it will bend like this. And the radius of curvature of this depends on this condition. So you can also think in this way. So what do you mean by radius of curvature? Clearly, can you show it? This is the alpha of brass, alpha of steel. This will be the radius of curvature. Small, all these are ideas, are not better, don't call concept also. Agreed? Huh? So these are things try to remember. Next year, this particular ball, it is just able to pass through the ring at temperature T1 degrees Celsius. Then I'll increase the temperature. Now the ball is unable to pass through it. The reason for that, the ball will expand more than that of the ring. So alpha of the ball is alpha of the ring. So here what is the B? The radius of the ball B equal to R into 1 plus alpha of ball delta theta. Even the ring also will expand. A is equal to, this also R 1 plus alpha, that of the ring R delta theta. Who will expand more? Alpha B is greater than alpha R. Then the ball will fail to expand here. Like this we can find out the alpha of the material. So there's one simple idea. So if I increase the temperature, the ball fails to expand. Both the ring and ball will expand. Now the ball will fail to pass through the ring. The reason for that, the radius of the ball will become now more than that of the ring at a higher temperature. If I decrease temperature at one temperature, then again it will pass through it. Then this we can write it A by 1 plus alpha beta delta T B by equal to A by 1 plus alpha R delta T. The unknown things can be determined. As we increase temperature, both X will expand, D will expand, R will expand. As temperature increases, X dash will become X into 1 plus delta T. R dash will become R into 1 plus alpha delta T. d dash will become d into 1 plus alpha delta. All will expand. The distance between any 2 points will increase. The gap will increase. The radius will increase. The width also will increase. So in thermal expansion, everything will expand. There's a basic condition. So we'll take the next one. There's a semicircular ring, that one. I'll expand it. So we'll take the points here, some points. There's a center O, radius is R. This is A, B, and D. I'll increase the temperature. Then center of mass will be here. What is the center of mass? Will be at a distance 2r by pi. What will shift? Center of mass will not shift. What is C? C is the rest. Everything will expand. All the points will shift except the center of mass. Center of mass will not shift. Remaining all points will shift, will expand. So what is the distance OC? Now this will become O dash, A dash, B dash. So what is OC dash? OC dash should be equal to OC into 1 plus alpha delta T. This is at higher temperature T2. This is at T1. T2 greater than T1. Now, small ideas. We are burning it. We are expanding it. Then what about OC? OC will be 2r by pi. Similarly, OA dash is equal to OA 1 plus alpha delta T. OA is R. All things will expand. Similarly, CB dash or B dash C equal to BC into 1 plus alpha delta T. What is BC equal to? R minus 2r by pi. Even it will also expand. All quantities will change. OD dash greater than OD. B dash A dash greater than B. Everything will expand. Center of mass will not shift. Only this will not shift. Different shaped objects you must learn here. Okay, so we'll discuss about the thermal expansion of solids and liquids. Here, effect of band force. If a liquid and solid both expands, what will be the length of immersed, fraction of volume immersed? Those ideas we will be discussing here. Now, initially at T1 degree Celsius, this is a cylinder of height h and radius r. X length of solid is immersed. Alpha is the density of the solid cylinder and rho L is the density of the liquid. Then what is the band force? Band force equal to density of liquid, volume immersed into G at T1 degree Celsius. Then it will balance the weight. The weight of the substance will not change because weight of substance equal to how much? M will not change, G will not change. So weight of substance will remain same. I'll increase the temperature. This is at T1 degree Celsius. At T2 degree Celsius, the new band force will be rho L dash Vi dash, the new volume immersed. But again, it will be like this only. So therefore, and what is the weight of solid? Will be mg. By equating these two, Fb dash equal to Fb, rho L dash Vi dash G equal to rho L Vi into G. Rho L dash will be rho L 1 plus gamma L delta T. What is the volume immersed? Volume immersed will be Vi 1 plus gamma S, that of the solid, into delta T equal to rho L Vi. There's a one basic condition. Okay, fine. Okay, sir, why you are equating? Okay, we'll do one thing. This may not be needed. So new bind force will calculate. FB dash equal to rho L VI dash G. What is rho L dash equal to? Rho L 1 plus gamma L delta T. What about VI dash? Bind force will have to remain same. Then this will become 1 plus alpha S delta T into G. So this is a basic condition. FB dash equal to okay. And I'll remove this part. Okay, this is a bind force. So bind force, will it increase or decrease? It depends upon this condition. Okay, then afterwards, what about the volume immersed? Volume immersed. So here we'll define the fraction of volume immersed. What do you mean by fraction of volume immersed? Fraction of volume immersed, K I'll call it. This should become X by H. What is the X by H? X by H will be equal to okay, this we have to write. Now K dash will be X dash by H dash. Xi dash. So fraction of volume immersed. I'll define that clearly. Fraction of volume immersed, which is equal to volume immersed by volume of solid. And this particular thing. Now even this will also change. Vi dash plus Vs dash. Okay, agreed. Next, the fraction of volume immersed, we can write it as this will be density of liquid by density of from the buoyancy, and this will be rho L dash by rho S dash. Rho L 1 plus gamma L delta T by rho S 1 plus gamma S delta T. So the fraction of volume immersed, we can write it as K dash equal to K gamma L into delta T. So volume immersed increases, K dash greater than K. If quotient of volume expansion of solid more than that of the liquid, then volume immersed will increase. These are the conditions. Similarly, K dash less than K, when gamma is less than gamma L. If the liquid expands more than solid, then definitely what volume immersed decreases. If gamma is equal to gamma L, then there won't be change in the circuit volume immersed. So this basic conditions, which is very important, you have to remember. Next we'll discuss the thermal expansion of liquids. A very simple formula based. Initially I'll fill up a liquid in a glass vessel, a conical glass vessel. The liquid is off to the level. So initial level is A. As I increase the temperature, initial temperature, let it be T1 degrees Celsius. At T2 degrees Celsius, the level will fall. The glass will expand. It's not that the glass will expand. The liquid is yet to expand. Whereas the glass will become Vs dash. The level will fall. Okay, then the level of liquid also will increase. Then that of the glass, this is at T2 degrees Celsius. So first here only glass expands. Both liquid and glass expanded. Liquid and glass expanded here. So what is the real expansion? The real expansion will be B to C. Apparent expansion will be A to C. This will be the real expansion. Apparent expansion. From B to C is what? Real expansion of the liquid. Actually, the liquid will expand from B to C. A to C is what? The apparent expansion. What was the initial level liquid at A, final level at C? So that was the expansion of the liquid with respect to vessel. What do you mean by apparent expansion? Expansion with respect to liquid. So how we write here? Expansion of glass or expansion of liquid with respect to glass, or expansion of liquid with respect to glass or solid. Gamma equal to expansion of liquid minus expansion of glass. What is the expansion of glass? 3 alpha G. This is called as apparent expansion. This is called a real expansion. Real expansion of the liquid, apparent expansion of liquid. Apparent expansion of liquid. Real expansion of liquid. This is the real expansion of solid or glass. We cannot find out. This cannot be calculated. This cannot be determined. Only can be calculated, or is not measurable. This is measurable. This is measurable. But this can be calculated. Like this, we can find out the real expansion of the liquid equal to apparent expansion plus real expansion of the glass. There's a generalized formula which you can remember. Very less number of problems are there, but there's a one general conclusion for what you can make it. Next we have I'll fill up a liquid, fully filled up. Here liquid is fully filled in a vessel. So let gamma L be the coefficient of volume expansion of the liquid, alpha be the coefficient of volume expansion of the glass. I'll increase the temperature. No overflow. So no overflow means how much liquid expanded, that much volume expanded. So here gamma L equal to 3 alpha G. 3 times of volume expansion of the glass. Here. Similarly, here the temperature is increased, the level will fall. You can see fully filled up, level will fall. Here who has expanded? The glass has expanded more. So gamma L less than 3 alpha G. Then here overflow. Liquid overflows at higher temperature. Then the liquid has expanded more than that of the glass. Like this, small ideas try to remember. You don't get any very big problems, small ideas only. No. Initially, m naught mass of the liquid is fully filled up in a vessel at theta 1 degree Celsius. Hmm. Now let gamma L be the quotient of volume expansion of the liquid. It's a real expansion, which we cannot determine, only it should be calculated. But what we can calculate? Apparent expansion we can calculate. I'll increase the temperature. Liquid will overflow, some liquid will be expelled. Remaining will be liquid present. Then the apparent expansion, quotient of apparent volume expansion equal to mass of expelled liquid by mass of remaining liquid into rising temperature. Mass of expelled liquid mr into delta T. What is the m naught? M naught should be equal to mr plus me, no? Mass of the remaining liquid plus a mass of expelled liquid. So this me, what we can write, m naught minus mr. So there is one formula. Now apparent expansion equal to mass of the liquid by mass of remaining liquid minus 1 into 1 by delta T. Delta T is the rising temperature. Theta 2 minus theta 1. We'll get apparent expansion. We know volume expansion of the glass. We'll get the real expansion of the liquid. These are the type of problems what you can expect. More than this not needed. Just remember only this much. Okay kids, so this is thermal expansion of the liquid. Small formulas. There's a one formula which you have to remember. There's a one formula which you have to remember. Rest of everything you can manage. Okay, we'll take the next topic. Next we have the calorimetry. There's a specific heat capacity definition we'll define. This is defined as amount of heat supplied per unit mass per unit rise in temperature. Amount of heat supplied per unit mass per unit rise in temperature, we define that as specific heat capacity or specific thermal heat capacity, either of one. So this will become calorie per gram per degree Celsius, or unit will be joule per kg per degree Kelvin or per Kelvin. Okay, this is the unit. Mostly we'll be using the particular the CGS unit only for convenient purpose. So here I'll supply the heat. Then the temperature of body will increase. Then equal to the formula Q equal to ms T2 minus T1, where S is the specific heat. Specific heat capacity for different substance it will be different. This is a general formula which you have to remember. And we know 1 calorie is equal to 4.2 joule, where all the conversion will make it here. Then this mass into specific heat will bring the next quantity called as heat capacity. Symbol will be H, which is mass into specific heat. The unit for this will be calorie per degree Celsius or joule per Kelvin. Mass into specific heat of substance is called as a heat capacity or thermal heat capacity. Now, what do you mean by a calorimeter? Calorimeter, it contains the copper vessel. This is the inner vessel made up of copper. Usually this is made up of copper. There is air space. The outer, this will be made up of wooden coating. There's an inner vessel. There's made up of copper. Will be in cylindrical shape. There's a thermometer to measure the temperature. There's a stick and there's an insulated lid. Air gap will be there, and here the wooden coating will be given, which will give the outer vessel will be wood, which will provide the insulation. Here some air gap also will be there. So this is a basic idea of the calorimeter. Whenever I discuss the calorimeter, this is the contents of calorimeter, or say mixture of calorimeter. Some different substance will be added, and I want to know that what is the temperature of the mixture. Okay, fine. This is a mixture, liquid, solid, ice will be added to water. This is a thing. Then we'll discuss the next condition, water equivalent of calorimeter. What is the biggest problem is this calorimeter will have the mass of copper and is made up of specific heat. Usually made up of copper. How to find out that one? I'll consider the equal amount of water. Specific heat of water will be 1. We know specific heat of water will be 1 calorie per gram per degree Celsius. I'll supply same amount of heat. Both are at same temperature. T1 degree Celsius. This is some water. And I'll see that both will attain same temperature. Both will have same temperature. So this shows that so what is the Q? Here the Q supplied, mass of calorimeter, specific heat of calorimeter, T2 minus T1. This should be equal to mass of water, specific heat of water, T2 minus T1. So therefore the specific heat equal to this much. What is the specific heat of water 1? So this is nothing but equal to amount of water. This is called like a water equivalent of calorimeter. So that will be in terms of gram, wrong unit. Okay, no problem. Where all mass of calorimeter, specific heat of calorimeter, you have to substitute with water equivalent of calorimeter. There's a small idea. Next we have the principle of calorimeter. Heat lost by one body equal to heat gained by other body. This is one basic problem solving we'll be doing. There's a hot body at temperature T1 having mass M specific heat. There's a cold body having mass M2 specific heat S2 at temperature T2. T1 greater than T2. Both will come in contact. There'll be flow of heat from the hot body to cold body. So this body will lose heat. Loses heat. This gains heat. So heat lost by one body equal to heat gained by other body. How much of heat lost? M1 S1 T1 minus T. There's a heat lost by this body. How much of heat gained? M2 S2 T minus T2. So then this will become M1 S1 T1 plus M2 S2 T2 equal to M1 S1 plus M2 S2 T. Solving for the temperature at equilibrium is given by this formula. Okay, the heat lost by one body equal to heat gained by the other body. From this we can calculate the temperature at equilibrium. There's a generalized formula, try to remember. A certain block whose specific heat will vary with the temperature of this block. It is added to the hot furnace whose temperature is T2, T2 greater than T1. Then finally it will attain temperature T. So what is the time it will take? At T equals 0 drop after some time T. We can calculate this time. Then here also the same condition. The heat lost by the hot furnace should be equal to heat gained. What is the heat gained by it? But what to do here? We are having specific heat varying. So here we'll write here dq equal to ms dt. What is the specific heat? The specific heat is varying with the time or with the temperature. So the total heat gained will be equal to m1 a plus b dt. 0 to q equal to, this will be 0 to t. This will become q equal to m1 at plus BT square. So this is a heat gained by the body. Yeah? Now, what is the heat lost? The same heat is lost by the this hot furnace M2S2 T2 minus T. We'll equate these two. M2S2 T2 minus T equal to M1. Solving for T, we'll get the required answer. Like this, specific heat of substance can vary with the time. Sorry, can vary with the temperature. What is the T? T is the temperature. Small ideas, very, very, very important. There's a along y-axis the temperature, along x-axis we have the heat input. So here what I supplied is like a m grams of ice is present, m grams of ice. It is supplied heat. It will become water at 0 degrees Celsius. For here we'll supply the heat Q1. Then I'll supply further heat. It will become water at 100 degrees Celsius. If I further supply heat, steam or vapor, vapor at 100 degrees Celsius. So that particular thing is called as Q1 here. Okay, this will be Q2. This will be Q2. This is some Q you can call. Here actually the ice is at minus 10. Initial will start from here. M grams of ice. I'll supply heat. There's some Q naught. Ice at minus 10 degrees Celsius. I supply it. Then will become water at 0 degrees Celsius. So ice at 0 degrees Celsius. Further, when you supply it Q1, will become water at 0 degrees Celsius. Further, you supply it will become water at 100 degrees Celsius. Further, when you supply it, will become vapor at 100 degrees Celsius. If you further supply it, as the vapor, temperature of vapor will increase here. This is the basic idea. All these things are Q0, Q1, Q2, Q3. Okay, no. So what is a Q0? You can write it. Q0 is equal to M mass of ice into specific heat of ice into dt. So what is this dq0? Will write it dq0 by dt. So what is tan alpha 1? Tan alpha 1 will write it as dt by dq0. So therefore, the reciprocal of slope will give the thermal heat capacity of the ice. Then what is AB? QAB. QAB will define it. QAB or Q1 equal to M into LF. Similarly here, dQ2 is equal to M into specific heat of water into dt. Tan alpha 2 is equal to dt by dQ2 equal to 1 into M into specific heat of water. Then QCD equal to Q3 mass into latent heat of vaporization. dQ3 equal to further dQ4 here at this particular point. Q4, if you want to increase the steam further, you can some temperature, mass into specific heat of steam into dt. So therefore, what is the reciprocal of the slope? Reciprocal of slope will give the thermal capacity of the substance in the solid, liquid and the vapor state. And what is this horizontal length of this will indicate the measure of vaporization. The ratio of CD by AB will give LV by LF. So lot of information is available in this particular graph, which you have to remember. Next is just some amount of ice. This ice added to the water. Ice added to water. What will be the finally what will happen? How much of ice will melt? How much of water will be present? That we have to determine. So now, what is the T? T is greater than 0 degrees Celsius. The temperature of the water is greater than 0 degrees. Let it be 10 or 5 degrees Celsius. Ice is at 0 degrees will be added. What is the mass of ice? M2. Mass of the water in the calorimeter will be M1. And water equivalent calorimeter is WC. Definitely now who will lose it? The calorimeter and water will lose it. And who will gain? The ice will gain. I think this is what happens now when you add some ice blocks to the juice. Sometimes the whole ice will melt. Sometimes the whole ice will not melt. That's what we are discussing here. Simple. Nowadays, anyway, this is summer. When you add some amount of water, some amount of ice to the water become cold, no? This is what we'll be discussing here. Fine. So now the heat lost by the water in calorimeter should be equal to heat gained by the ice block. Heat lost equal to heat gained. Heat lost. Who will lose it? The water. M1 specific heat of water. T0 minus some temperature. Finally, it attains some temperature. But water equivalent of calorimeter. MCC. It is also. This should be. This is the heat loss. Heat gained by the first the ice at 0 should melt. Mass of ice. Mass of ice is M2. LF. Then M2 into specific heat of water. Its temperature will rise to certain value. T minus 0. So we are assuming the whole ice will melt. Here what is the ice added to water and whole ice melts. Only sir if a part of ice will melt. If part of ice will melt means in that case what should happen? The temperature of water should become that of 0. Then the next situation, next you can see that when the all ice T naught greater than 0 and finally the temperature will be greater than 0. The whole ice will melt, and what all the ice will melt, that will form a water of mass M2 here. We are assuming this one. The data will be given. According to that, we have to work out here. Similarly, ice block is added. Now the whole ice will the whole ice will not melt. Ice added to water, so we'll write the condition. Ice added to water and part of ice will melt. So what are the conditions for this? If only we added ice block, only a part of ice block will melt here, and the final temperature should become 0 now. Why it should be 0? Because ice at 5 degrees, 6 degrees not possible. So what should be the final temperature? If some ice left over, the final temperature should be 0 degrees Celsius. Now we'll lose it, the calorimeter. Heat lost equal to heat gained here. What is the heat lost? Mass of water, specific heat of water, T naught minus 0, initial temperature. Calorimeter, T naught minus 0. This will be utilized to melt some ice. M2 dash mass of the grams, M2 dash grams of the ice will melt here. The remaining mass will remain as it is. Only how much it will melt? M2 dash here. So now, can you calculate M2 dash as here from all this we know? Once you know M2 dash, then you can write M2 as M2 dash plus M2 double dash. Try to understand concept. If I solve problem, you'll understand and forget. This idea I'm generating. So if all ice melts, then the final temperature of water can be greater than 0 or equal to 0 something. Here, if only part of ice melts, then final temperature must be 0 degrees Celsius. So the temperature of water in calorimeter will decrease, that will be absorbed by the ice, and that amount of heat will be utilized to melt a part of ice. Then we can calculate the remaining amount of ice, how much left over. Next we have the ice block. We are going to add up the steam. Some M2 grams of steam at 100 degrees Celsius will be added to the ice block at 0 degrees Celsius. It's kept in a calorimeter. Water equivalent of calorimeter is WC. Then we will lose, the steam will lose heat. The heat lost by the steam will be absorbed by the ice block. First ice block will melt, will become water at 0 degrees Celsius. Then again the both calorimeter and water's temperature will rise and will attain some temperature T. And the steam first will condense, will become water. Again from water at 100 degrees, M2 grams of water at 100 will become certain temperature. So the steam will lose heat lost. Q1 equal to M1 into LV. Then again, what all it becomes 100 grams of water, they'll be converted. Again, temperature has to decrease. So this will become M2, mass of steam is M2, some correction, M2 into specific heat of water 100 minus T. Final temperature, this is the mass of the water which is formed due to condensation of steam. What is this amount of water formed due to melting of ice? I'm just explaining some idea. Sir, why only like this? It all depends on the data, initial temperature, masses of this one. Then heat gained. Q2 equal to, who will gain it? The amount of water. First ice will melt. Then the specific heat, then amount of water formed due to melting of ice. So temperature from 0 will become 100. Then this calorimeter, its temperature will change from, okay, it will be like a T minus 0. Okay, if all the data are given, we can calculate the temperature T. Or it's possible that some amount of steam only will If some amount of steam only will condense, then the final temperature will be 100. It all depends on data. I'm just sharing some idea. So when steam come across the ice block, okay, there's a basic condition. Next we have the triple point of the water. I'll fill up like a water in a glass vessel. I will slowly decrease the temperature. I'll also decrease the pressure exactly at 0.01 degrees Celsius and at the pressure 0.6 kilopascal, less than atmospheric pressure. I can see that here steam, ice and water, all three will coexist in a vessel. So steam at 0.01 degrees Celsius is possible. All will coexist. This is called like a triple point of water. That will be fundamental. Zero is not fundamental. The triple point will be fundamental and it will not vary. Pressure, you change pressure, anything, it will not change. Whereas the melting point and the boiling point, they are not fundamental. They'll vary with the pressure. So you can see like when the ice will melt, we think that at zero. No, by varying pressure, even at lower temperature also, we can, even at 2 degrees Celsius also ice is possible. Even water at -10 is also possible. 0.0 like a 0.6 kilopascal it is. Like this is what the triple point of water. It's a fundamental. Or in terms of this 0.01 I took it 0.0098. And this become reference point. This will become fundamental. All three states will coexist here. Then what is the condition? Then we know that to freeze, to melt an ice, what we should do, we should supply the, to melt an ice, what is the basic idea? We should supply the heat. No, I can melt the ice even by I can melt the ice by melting. For that what we should supply the heat. Or by how to convert the water to ice? By freezing. Then I can convert the liquid directly, so the liquid to the solid. This will be better, say ice, water, this is a gas or say vapor. By varying pressure. By varying pressure I can convert directly the water to the ice. That is called like a deposition. I can melt the I can melt the ice by sublimation. For that what I should do? I should decrease the pressure. Similarly, by increasing pressure I can melt the ice to the water. If I decrease the pressure, the water will become the ice. That's called like a deposition. So what is the deposition? Deposition, converting the ice to different, means by changing the pressure we can melt the ice. By increasing the pressure we can melt the ice. By decreasing the pressure we can freeze the water. What is the vaporization? Converting the water to the vapor, called as vaporization. For vaporization what is needed? You have to supply heat. But here can I do one thing? By varying the pressure. By decreasing the pressure the water will become vapor. By increasing the pressure the vapor will become water. The same situation here also. By decreasing the pressure, the ice will become water. By increasing the pressure, the water will become ice. Or by decreasing the pressure, the water will become ice. By increasing the pressure, the ice will become water. We can convert ice to the gas also. That's called a sublimation. And gas to the ice. This is called a deposition. So these conditions are very important. So one important idea we have brought it here. How to convert water to ice by decreasing pressure. Similarly, ice is there, you can convert into water by increasing pressure. Yeah, there's a simple idea, sir. So this can you freeze water by taking out it? No. Instead of taking out it, what will happen? Just what you can do, decrease the pressure, the water will become ice. By increasing pressure, the ice will become water. This is one basic idea of the triple point of water. Not very important, just have a small idea. It's a fundamental which will not vary with pressure, whereas the melting and boiling point will vary with the pressure. More than this, not needed. Okay. This next topic we have the thermal conduction. This is again a very simple topic. Moreover, the thermal electrical resistance, based on that is what the thermal conduction problems will be asked here. Now there's a candle flame. There's a candle flame. There's a metal rod. There's like I say copper rod. At one end we'll supply heat. Then we can see that the heat starts flowing from one end to other end. At other end, we can feel this hot sensation. If you hold this rod, copper rod for 5 or 10 minutes, no, you can feel this end also becoming hot. But actually you are far away from candle. This distance like a 2 meters. I think we're very far away. No, the candle flame will not supply any heat to the hand. But how this heat, the hand will feel the heat because the copper rod will transfer it. There's a basic mechanism here. Means the copper rod will be involved in the transfer of heat. Inside the copper rod will be there the atoms and the electrons. There's the hot body and there's a cold body. So here the hot body, here the atoms will vibrate and those atoms will transfer the energy to the adjacent atoms. The adjacent atoms will accept that energy and will disturb the next beside atoms. So like that there will be transfer of energy from one atom to other atom from the hot to the cold body, and the free electrons also responsible. Free electrons will move randomly but the net flow will be towards right. Now this atom vibrating will collide with the next adjacent atom. So it will transfer its energy to it. This atom vibrating will transfer to the next atom. This vibrating atom will disturb the adjacent atom and will transfer that mechanical vibration. Like that, the heat what happen will flow due to the vibration of atoms and the free electrons. Free electrons will move left and right, but the net flow will be from hot body to the cold body. Suppose there is a cold body, there is hot body, there is a cold body. The heat flow will occur T1 greater than T2. Similar, the same thing. There is a hot body, there is a cold body. This is having a length L. So here we can divide this into segments. Some segments I'll divide. Then there's a temperature T1, T2. The atom which is here vibrating, it will disturb the adjacent atoms of this rod. These atoms here also start vibrating. They will acquire temperature say Ta. Then this vibrating atom will disturb the atoms present in this. So this will also vibrate the atoms here. This will acquire temperature Tb. Here this will acquire temperature Tc. Here Td. Here T. And these vibrating atoms will disturb the atoms in the cold body. So here also they'll start vibrating. This is a basic idea of the heat transfer. How you measure the temperature? The degree of the amount of vibrations of the atom. If vibrations are more, if the frequency of vibration is more, then it is said to be at high temperature. Then we'll get the temperature gradient across the rod. As we move from hot to cold end, This will be the temperature gradient. What actually happens? This will transfer it to this. This will absorb it. It will acquire some temperature. Afterwards, at steady state, no longer absorption of heat. What is this first element A? It will absorb it. First it will absorb it. It will acquire some temperature. Afterwards, when it acquires certain temperature TA, it will not be involved in the absorption of it, only involved in the transfer of it. Similarly, the section B will absorb it. After attaining certain temperature, it will be involved only in the transfer of heat. So like this, there will be flow of heat from hot body to the cold body. This rate of flow of heat is equal, depends on what? Coefficient of thermal conductivity, area of cross section, temperature difference, and the distance. This is nothing but we'll call H, where K is called as coefficient of thermal conductivity. Q is the heat flowing per unit time. So this will become thermal power flowing through the rod depends upon coefficient of thermal conductivity, and this will be different for different material, area of cross section, and temperature difference, and inversely proportional to the length. It will have a negative temperature gradient, or we can also write this as minus Ka. Now when to use this formula? If K and A are varying, we use this formula. If K and A are constant, we use this formula. Okay, done. So who is responsible for flow of heat? The atoms, vibrating atoms, and the free electrons. Both are responsible for flow of heat across the rod. This is what happens in the thermal conduction. Now this is the hot body. This is the cold body. The heat will flow in this direction. Yes. Who is responsible for? And there is the area of cross section. Then the amount of heat flowing per unit time, dq by dt, which is equal to Ka T2 minus T1 by thickness, or this is nothing but equal to H. K is the thermal conductivity. For different materials will be different here. So what is the unit for K will be joule, or say watt per meter per Kelvin. There's a value of quotient of the unit for quotient of thermal conductivity. This is the called as rate of flow of heat, or you can give name thermal power, or you can also call it as heat current. So based on this, we can write it as Ka delta T by D, or this will become delta T by R, where R is called as thermal resistance. Who will offer this thermal resistance? Resistance offered by the material to the flow of heat. The heat will not flow easily. The material will offer the opposition to the flow of heat. That is called like a thermal resistance. And thermal resistance depends on what? Depends upon the thickness, K, and area of cross section. And the heat will flow from hot body to cold body. Who is responsible for flow of heat? The atoms, vibrating atoms, and the free electrons. That's a general idea. And we are discussing at steady state all these things. What do you mean by steady state? No absorption of heat by the rod. There is one more condition. This is very, very important. All our discussion will be based on this one only. Thermal resistance, they are in series. When they are in series, we have to calculate the effective resistance. Let the thermal resistance of this be R1, let this be R2. Then the same heat current, same thermal power will flow. And when you can say this is the equivalent of it, when you can say this is the equivalent of it, what amount of heat transferred by these two rods, same amount of heat this rod should transfer it. Then only you can solve this is the equivalent of it, and connected across the same source and the sink. What do you mean by source? It will supply heat, but temperature will not decrease. What is the sink? It will absorb heat, but its temperature will not increase. This is the meaning of source. T1, T2. This will be candle flame. This will be some water bath or some amount of water. So large amount of water. So though it will absorb heat, temperature will not increase here. This is the meaning. Once again, I'll repeat. Source means supplies heat, temperature will not decrease. Sink means absorbs heat, temperature will not increase. Now, since the heat supplied is same, let T be the temperature. Then the temperature difference T1 minus T2 is equal to T1 minus T2. What is T1 minus T2 from here? Heat current H into R. This will be T1 minus T plus T minus T2. What is T1 minus T? The temperature difference across this equal to heat current into resistance. This will be heat current into resistance. R equal to R1 plus R2. So when the two rods are in series, same amount of heat current will flow. The amount of heat flowing per unit time will be same. What is the effective thermal conductivity? Effective thermal conductivity will be L1 plus L2 Ka is equal to L1 by K1A L2 by K2A. You can remember these things, very useful for you. So what will be the thermal conductivity of this rod? Equal to this much here. No absorption of heat. How to calculate the temperature of junction? I think you can calculate the temperature of junction also. The temperature of junction, we can use this formula. T1 minus T by R1 equal to T minus T2 by R2. T1 R1 plus T2 R2 is equal to T by 1 by R1 plus 1 by R2. Temperature of junction T1 R2 this will be the temperature of junction, like this is the junction. Okay, now we'll go for the parallel. What do you mean by parallel? Across the hot and the cold body, we are there's a cold body. What do you mean by parallel connection? Across the hot and cold body, two rods are connected. They're having the length, and this will also have the length L. And the area of cross section, this is A1 plus A2. This will transfer some heat. This will transfer some heat. What heat, what thermal power these two rods together transfer, the same thermal power they should transfer. Then you can say this is the equivalent of this one. the thermal power, the heat energy will flow through here, here also will flow through here. When you can say this rod is equivalent of this, what power these two together, these two rods will transfer across the hot and cold body, the same power they should transfer. H equal to H1 plus H2. What is H is equal to? Temperature difference T1 minus T2 by R. R be the resistance. H1 equal to T1 minus T2 by R1. T1 minus T2 by R2. 1 by R equal to 1 by R1 plus 1 by R2. This is a thermal resistance. Okay, how to calculate the equivalent? This will be Ka. This will be equivalent thermal conductivity. Then what is H1 here? H1 will be delta Q1 by delta T1. Amount of heat. H2 equal to delta Q2 by delta T. Same amount of heat will not flow in a given interval of time. If the heat flow here, heat H is thermal power, Q is heat. So the amount of heat flowing will be different. Okay, fine. So here this delta Q1 depends on what? The thermal resistance again. So here, like I suppose H1 greater than H2, then delta Q1 should be greater than delta Q2. The heat flow across the rod will be different, and the thermal power will be different here. In a given time, here if it more heat flows, here less heat will flow. There's a basic idea. I brought some. There's a hot body, there's a cold body, and there's a rod. So then we'll calculate the heat current, which is equal to Ka T1 minus T2 by L. K is how much thermal conductivity of the rod, 4 watt per meter per Kelvin. Area of course 10 centimeter square, 10 into 10 to power of minus 4. Temperature difference 400 minus 300 by length is 2 meter. This will be 100. This will be 0.2 joules per second. Here 100 will come, 10 to power of minus 0.2 joules. What do you mean by that? For every 1 second, 0.2 joules of the heat will be transferred by the rod. In 1 hour, how much it is? In 1 hour, it will be 3600 seconds. Then total heat transferred by it will be H into delta T. H is how much? 0.2 into 3600. 720 joules. This much of heat will be transferred by the rod. And where do that heat? It will flow here. There's a basic learning. First try to learn. Everything will become easier. What this rod will do will transfer it. This much of heat is transferred. It will not transfer it suddenly. Are you getting this one? This is the thermal power. This is thermal power. This is a heat. This much of heat will be transferred. It will in 1 hour by the rod in 60 minutes. So will it and will it absorb it? No. And what about the temperature? As you move from here to here, it will decrease. What is the temperature here? Here it will be 380 Kelvin. Here temperature will be 360 Kelvin. Here temperature 350. Here 330. Here 310 Kelvin. And what about the rod? Rod will not absorb it. It is transferred by the rod, not absorbed by the rod. There's a fundamental idea. Try to remember this, rest all you can manage. The rod will be transferred. We are discussing at all our discussion is at steady state only. Okay. Huh? Next we have the three rods are they're connected here. This end of the rod at temperature T1, T2 and this is T3. We have to calculate the temperature of the junction. Here heat will enter here. Here heat will enter. Here heat energy will be H1. So conservation of energy principle. How much of heat enters per second? That much of heat should leave per second at the junction. So H1 plus H2 should be equal to H3. What is H1? Heat transfer. So T1 minus T by R1. What is H2? Heat transfer here. T2 minus T by R2. This will be T minus T by R3. T1 by R1 plus T2 by R2 minus okay, this will be plus T3 by R3 equal to T1 by R1 plus 1 by R2 plus 1 by R3. Okay, this will be, so now we'll get the expression for temperature. R1, R2, R1, R3 plus R2, R3. Substituting all these values, what is R1? R1 will be L1 by K1A. R2 will be L2 by K2A. R3 will be L3 by K3A. Okay, these are the thermal resistance. This is the temperature of the junction. Here the heat current H will enter and it will leave at this particular point. We have to find out the temperature of this junction. Area of cross section of the rods, all are having area of cross sectioning and the dimensions are given. Thermal conductivity like this. We have to calculate the temperature of this junction. Okay, fine. So what all the heat current enters here? Some heat current will pass like this, H1, and the same heat current will come here, H1, here H2. Okay, agreed. Now we have to calculate the temperature, this particular temperature, and we know this temperature difference. How these two rods they are in series, same heat current will flow. So therefore, based on that, 3T minus T naught by this resistance. Resistance of this rod will be 4L by 2KA is equal to T naught here. This heat current. What is this heat current should be equal to T naught temperature, T naught minus 2T by 5L 3K. What is the length of this will be? Three L whole square, 4L whole square. This is the length X I'll call it, where X will be 5L. Okay, this will become 3T by 2 minus T naught by 2, 3T naught by 5 minus 6T by 5. Solve for this T naught, will get the required answer. This is the temperature of this end corner, you can call anything. Different shaped rods. So what is the idea from where you are writing? This H1 should be called H1. What heat flows here? The same heat will flow because these two are series. So what about here, sir? This one, this H2, because the current comes here will branch, similar to electric current. Now instead of heat current, I'll ask you to find the ratio of heat flown across the rod. What is H1 equal to? T1 minus T2 by R1. H2 equal to T1 minus T2 by R2. H1 R1 equal to H2 R2. What is H1? Heat flow, no? Q1 by delta T. R1 is L by K1A. K1A1. This will be Q2 by delta T L by K2A2. Q1 by K1A1 equal to Q2 by K2A2. So the ratio of heat flown across the rod, the heat flown across the rods will be different. What is this ratio of heat flow? Try to bring that idea, heat flown. We are discussing about the amount of heat flown through the rods. What this rod will do will transfer heat. How much of heat? So how much of heat transferred? Q1 by Q2. It depends on K1A1, K2A2. Now there's a concrete wall. Usually for house, inside the insulation will be provided, outside insulation. Then the heat energy will pass. So T1 greater than T2. The same heat current will pass through it. Then we can calculate this temperature difference. So what is H is equal to? H is equal to, according to this will be T1 minus TA by the resistance of this. The resistance of this will be, thickness will be A by K, area of cross section. Similarly, this should be equal to TA minus TB, the thermal resistance of concrete wall. Thickness of this will be B, 3Ka by B. This will be TB minus T2, thermal resistance of this, C by 2Ka. We can calculate the temperatures of these things. If you know H, you know T1 will get TA, similarly we get TB, then we can calculate the temperature difference. In general, the widely we'll be using in our applications, especially for air conditioners. The inner wall I'll insulate, outer wall also I'll insulate. Then the heat flow has to be blocked here. No, thermal resistance of different shaped objects. There's a truncated cone. We have to calculate the thermal resistance. So the temperature of this can be T2, this is T1. So here we'll write condition T1 greater than T2. This is the axis. How to find out here? How the heat will flow along the axis. So normal to this, I'll assume a surface here. So fine. So this is the heat will flow like this. Right. So this is the thickness. Let this radius be smaller. Okay, fine. We have to assume this disc, thin disc. What is the resistance of this? Will be dr is equal to thermal resistance of this, thickness dx k by pi r square. Fine. Then we'll get one triangle here. Call some alpha. This will be b minus a, r minus a. This is x. This will be l. So from the triangle r minus a by x equal to b minus a by l. Here we'll replace this one. So r equal to b minus a l x plus c. So dr is equal to b minus a l into dx. Substituting dx in terms of dr, then integrating. Then I'll get thermal resistance as L equal to K pi AB. Then how to calculate the temperature at a distance x? Same heat will flow. What heat flows as same heat? So this part and this part, they are in series. Then T1 minus T by left side, say R1. This resistance will be R1. This resistance, let it be R2. Should be equal to T minus T by R2. We can directly compare here. So what is the further T minus T by R1? R1 will be L by 2 K pi resistance. This will be A into R equal to T minus T2 L by 2 by K pi R into B. So this will become T1 minus T by A equal to T minus T2 by B. Okay, this is X. We'll take it X. X. This will be L minus X. Okay, now there's a solve for T. Like this, we can calculate the temperature at a distance X. The total length is L. So what about this length will be L minus X. If this is X, L minus X. So we can calculate the temperature at any point on the rod. Thermal resistance, this formula you remember, and there's a formula for temperature. Don't remember, just to have an idea. In exam, take help of this and solve it. Because it's very lengthy, you can't remember it. Now similarly, this is a thick shell. The inner surface at temperature T1, outer surface at temperature T2, where T1 greater than T2. How the heat? The heat will flow radially outward. Then here I'll ask you to assume a thin shell. Okay, fine. Here the thickness of this, let it be dx. Let the radius be x here. So what is the, and how the heat will flow normally, radially outward, better you can call. So the thermal resistance of this will be dr is equal to thickness dx k into 4 pi x square. So solving this, thermal resistance will be b minus a k into 4 pi ab. This will be the thermal resistance. Then how to calculate the temperature of anything? The same formula. Here what it will flow here. What it will flow. Suppose that this is say like you can break up this into two shells. Same heat will pass through it. So this will become T1 minus T by the thermal resistance of this part will be x minus a k into 4 pi xa is equal to T minus T2. Now from radius A to X, from A to X it will have one resistance. X to B it will have one resistance. We have to calculate the temperature at a radial distance X. So this will become B minus X K 4 pi B into X. So 4 pi X will cancel out. T minus T into A by X minus A. T minus T2 by again solve for T. Like this we can calculate the temperature at a radial distance X. What is X? X is the radial distance. The heat will flow radially outward here. And this formula you have to remember. And temperature at a radial distance X. These are the two ideas. Whether you understood or not, remember formula. We have the thick cylindrical shell. The inner surface of cylinder is at temperature T1, outer surface at temperature T2. The heat will flow radially or through the curved surface. These are insulated. This is insulated. So how the heat? The heat will escape now in this direction. Okay, fine. So this is the basic idea. Then we have to calculate it. So then the thermal resistance of this is given by the thermal resistance of this is given by 1 by 2 pi kl log of B by A, where L is the axial length, A and B are inner and outer areas, K is the thermal conductivity of material. They say low color one is the material which will transfer the heat. The same thing again, how to calculate temperature, the same approach you can develop here. Okay, fine. So these are the different shaped objects. You should know how to calculate the thermal resistance of the material. Now will vary with the distance x. This is x equals 0, this is x equal to 1. How to calculate the thermal resistance? So how the heat current will flow along the axis. So we'll assume here thickness dx, the heat will flow like this. Let A be the radius of this. Then the thermal resistance of this will be dr is equal to dx by k into A. What is k? A plus bx. So this will be 1 by A integral of dx so what is the this will be 0 to L. If the k varies, then this is a method. So this will become 1 by A B log of A plus bx 0 to L. 1 by A log of A plus BL by A. This is thermal resistance. What about heat current now? T1 minus T2 by R. If thermal conductivity varies, use this method. Assume a small element normal to the flow of heat, then integrate, we'll get the thermal resistance. Okay, next we'll have it will be varying with the temperature. One end of temperature T1, T2, thermal conductivity K. Let area of cross section A. Let L be the length. Okay, fine. Now we have to calculate how much of heat is flowing through the rod. Look at the temperature, it varies from one end to other end, and the thermal conductivity varies with the temperature. We know H equal to minus Ka dt by dx. What is K? A plus Bt, A dt dx. This will be H by A dx dt by A plus dt. So T1 to T2, 0 to L. So this will become HLA equal to minus of 1 by B log of A plus Bt T1 to T2. H equal to A by LB log of. So if the thermal conductivity varies with the temperature, this is a method you should apply. Okay, kids, we'll continue the thermal conduction problems. We have ice block of mass m and latent heat of fusion LF. It is 0 degrees Celsius. Other end of the rod, I maintain 0 degrees Celsius. I'll supply the heat. Then I want the time taken. Here heat is transferred. So let T be the temperature of this point. What about this point? It will be the length of this remaining length will be L minus X. Okay, fine. So here the heat will flow. So we'll call this as H1. The amount of heat flowing here will be H2. Okay, now what is H is equal to? First we'll write basic equation. H equal to H1 plus H2. What is the time this will take? So who is responsible? Here continuously heat will flow here. This H1 should be equal to K thermal conductivity K A temperature T minus 0 by L minus X. Agreed. So this will become KAT L minus X. What about H2? H2 will be KAT minus T naught into X. This is some general idea I'm discussing here. So if they give X, you can get the temperature T. At what distance? This one. Then for the whole ice to melt, we can calculate the whole ice to melt. The heat needed is M into LF. Then Q by delta T should be equal to MLF into delta T. What is Q by delta T? The heat flowing this side, this should become equal to H1. So this will become KAT L minus X equal to MLF into delta T. If I give X, I'll get the temperature T. The temperature T I'll substitute here, I'll get the time. So what is the delta T? Delta T is the time taken for all ice to melt. And these are some typical problems what you are going to encounter. What all we supply it, a part of it will move towards left, a part will move towards right. Then the ice will start melting. Similarly here we have there's a wire, highly conducting wire it is. This having thermal conductivity K. This end of the rod is maintained at 20 degrees, this is 30 degrees. From here the heat will flow. So what all the heat flows here? H. From here the heat will come H1. From here the heat H2. The heat flowing through the wire is responsible for melting of this ice. Ice is maintained at 0 degrees Celsius. Then this H should be equal to MLF into delta T. What is this H? Should be equal to H1 plus H2. What is H1? H1 will be 20 minus T, let the temperature here be Ka 20 minus T L by 4. What is H2? Ka 30 minus T 3L by 4. So this is the time taken for all ice to melt. All these are some simple idea based questions, are very important for mains advance. Both the ends of the rod are maintained at different temperature. Then in between somewhere ice block are connected. Then what time the ice block will take to melt. The heat supplied by this end and this end will be responsible. So from where this H2 will come? Here some source will be there which will supply the heat. Here also one source will be there. We can assume like this. Here we can assume one source. Here we can assume one source. These two are supplying the heat and their temperature will remain constant. Okay, we have to get the find the time taken for all ice to melt. At this end, at the left end, we are sending 200 calories per second. Okay, fine. This much of heat per second is introduced here. Here this end is maintained at 100 degrees. Here ice at 0 degrees is there. 3 rods are there. So we have to calculate the time taken for all ice to melt. Okay, let T be the temperature of junction. Here the heat current H1 will come. Will branch here. What all heat supplied H will branch here H1. The remaining heat will flow here. I'll show in the rods itself. So the heat supplied here H equal to H1 plus H2. What all heat supplied? H1 plus H2. What is H? H should be equal to Ka. Directly we know H. H is equal to how much? 200. Calories will be 4.2 joule substitute here. 1 calorie core 4.2 joule will be. What is H1? H1 will be K by 2A T minus 0 by L. H2 will be K 2K T minus 100 by L. Okay, we'll get the temperature T. After getting the temperature T, from here we'll get the T value. After getting T, then we can calculate H1 separately. What is H1 is equal to? H1 will be equal to this H1 should be equal to MLF delta T. We'll get the T. What is the delta T? Find the time delta T taken for whole ice to melt. Small ideas very important for mains advance. Then series parallel. Growth of ice layer in a lake. The temperature of the surroundings minus theta degrees Celsius. The depth of the water, let it be 0 degrees Celsius. Then during the winter season, this particular thing usually it happens in the Arctic region or polar region. In the polar region, the temperature of the temperature in the of water in the lake, pond, or in the sea or the ocean will be 0 degrees Celsius. As the winter rises, the temperature will fall minus T degrees Celsius. This will make it T as a temperature of surrounding. How much it will become? Minus Ts degrees Celsius. It will become minus 10, minus 15, we know in Antarctic regions. Then the water will lose heat. Then the ice, as the water loses heat, it will freeze. The topmost layer of the ice of the water will start freezing. This is the topmost. From here the water starts freezing. Now here an ice layer is formed. Now who is involved in the transfer of heat? The ice is involved in the transfer of heat, so it will involve in the transfer of heat. And I'm showing these arrows. These arrows are very important. Then we have other arrow. What is this? Direction of growth of ice. The ice will start growing from the top. Then we'll assume a small elemental area, thickness dy. Let y be the thickness. After some time, let y be the thickness of the layer formed. Then it's having thermal conductivity K. So first we'll find out the thickness of this one. Heat transferred, H is equal to Ka thermal conductivity of ice, A temperature 0 minus of minus Ts, into this will be L. Will transfer, there's a y, this particular thing. Then it will transfer the heat H. How does the heat H is produced? Because from where this particular layer, water layer of thickness dy, when it freezes, this much of amount of heat will be generated, which is equal to dq by dt. What is dq? dm into Ln. What is further dm? Density of ice, area of cross section into dy. Area of cross section will cancel out. This will become y dy equal to density of ice, latent heat of fusion, thermal conductivity of ice, and temperature of surroundings, and this will be dt. So this will become LS y square by 2. Okay, the time is proportional to y square. Remaining all are constant, independent of area. Time taken for the growth of ice layer in AT. What is t? Time taken for the ice layer to grow from 0 to y. So now you look at the 0 to y, y to 2y, 2y to 3y. The times are different. Time taken from y to 2y, 2y to 3y, 3y to 4. You calculate, the times will be different. Like this. This is time taken for ice layer to grow. Small ideas are directly formulas in exam. If they ask you based on this formula, you have to remember this limit. What all that limits they'll give. So this will be your formula which you have to remember for exam. Okay, fine. So kids, like so you have to put some effort. If you don't show interest in learning, not possible. You don't get rank. The major problem is like that you don't want to put effort and you want rank. Not possible. I'm scolding like this. Please try to understand. Your hard work will be proportional to rank. We have the ideal gas. It's having initial temperature T0. Outside temperature is surrounding. This is the cubical metal vessel. Inside that ideal gas is filled up, monatomic gas and moles of ideal gas, having initial temperature T0, pressure P0. Initial pressure P0. Outside temperature Ts, which is T0 will be greater than that of the temperature of the gas. So the initial temperature of the gas will be that of the surrounding. So as the temperature of surrounding is more than that of the gas, the heat will flow from surrounding into the chamber. So it will start flowing in from all the 6 phases. Here the heat. Okay, agreed. So from all 6 phases, from all 6 phases the heat will enter. Then this S should be equal to K6A, temperature of the gas at any time. This is T equals 0. At any time T, this is T. So temperature of the gas, temperature of surrounding minus temperature of gas by thickness D. Why 6A? All 6 phases, through the 6 phases the heat will enter. This should be equal to dq by dt. 6KAD Ts minus T. dq equal to ms. Okay, this will be ncv dt. Why ncv dt? It will undergo isochoric process. Thermal conduction mixed with the thermodynamic process. I am just bringing one problem. dq equal to ncv dt. This is dt. This will become 6KAD Ts minus T. This will be initial temperature T0, final temperature T. 0 to T. Log of Ts minus T minus with everything alpha T. This negative sign I'll send it here. So this will become Ts minus T equal to Ts minus T0 e to power of minus alpha. like this, the temperature of gas will increase with the time. So if you plot the graph, graph will be exponential. Okay, great. Huh? So these are some thermodynamics mixed with the thermal conduction. Here we discuss the thermal conduction with isothermal process. A very good problem. Simple, beautiful concept. You have to just first watch, learn it. It will be very useful for you. Now the temperature of the surrounding, it is greater than that of the insulating cylinder. Temperature of surrounding more than that of the gas. Then the heat will flow through the piston. So there's a piston, conducting piston. From where the heat will pass through the piston. Then what is the heat transferred by the piston? H is equal to Ka Ts minus T by thickness of this, let it be T. Let T be the temperature at any time T. Then who will transfer the heat? This thermal conducting piston. And we know in isothermal process, dq equal to dw, very super idea. Books not there, just I wanted to help you that one. So where the dq will flow here, the heat will flow here. And we know in isothermal process, if a gas absorbs heat, it will expand, it will undergo thermal expansion. Initial volume V, final volume V. Initial pressure P0, final pressure P. Here V will be greater than V0, P will be less than P0. Okay, fine. So here now, what is the pressure force? The pressure force will be acting like this. Where on the piston. Because of that, it will accelerate. Now, this dw is what? dq by dt should be equal to dq by dt. This should be equal to dw by dt. Rate of change of work energy. So this will be mv square by 2. Change in kinetic energy by derivative of it. dq by dt is what? The h. So Ka Ts minus T by D. The temperature will remain constant. Isothermal process, no? All these are constant. Derivative of this mv 2v dv by dt. So this will become Ka Ts minus T naught d mv into E. What is the speed of this one? What is A? A will become acceleration. It will start accelerating. And V is the velocity at that particular position. If I give the speed, you'll get acceleration, or if you get acceleration, you get the speed. Then, okay, sir, how you find out? We have the formulas. We can use it here. What is V? V volume, not velocity. So these are small ideas I shared it. V is the velocity, V is the speed, small v is the speed, not volume. A is the acceleration. Why it like that? Because of the difference in pressure force. Now this thermal conducting rod is connected across hot and cold body. This is the source, you can see. This is the body. It will absorb, it will receive the heat. The heat will flow from the hot body to the cold body. Let T naught greater than T. This is a source which will supply heat. The heat will flow from the source to the body. That one body is having temperature T, mass m, and specific heat S. Then what is this? H is equal to Ka T naught minus T by L. What is H equal to? dq by dt. Ka T naught minus T by L. dq further, the heat received by the body in interval of time dt. This should be equal to m specific heat dt. This will be KAL. Now this will become dt. Temperature of the body initially, let it be say like a T1. After some time let it be T this one. Let it be TS, initial temperature. This will be negative sign 0 to T. So this will become minus log of T naught minus T, T naught minus Ts equal to alpha T. T naught, okay, this is like a T naught minus T. E to power of minus alpha T, or T equal to T naught plus T naught minus Ts. Like this, the temperature of this body will increase exponentially. Similarly, we are having this. It can be gas, hot body, anything. Initial temperature T1, T2, having mass M1, specific heat S1, M2, S2. Then T1 greater than 2, the heat starts flowing. Then with the time, the temperature here also will the temperature difference will decrease. Here also the temperature difference T is equal to initial temperature T minus T naught e to power of minus alpha T. The temperature difference between the bodies with the time will decrease here. This is the hot body, we'll assume. This is a cold body. Then from where the heat will flow from hot to the cold body. The temperature of hot body will decrease, the temperature of cold body will increase, the temperature difference will decrease. What is T? T is the temperature difference. Lengthy derivation is there in JEE Advanced also. Better remember, this will be more useful. Okay kids, the next topic we have the thermal radiation. Very small topic and very important for mains as well as advanced. A purely simple formula based questions will be asked. So first we'll discuss the thermal radiation. Now this is the air, the surrounding temperature of the air, let it be 20 degrees Celsius, 25 degrees Celsius. This is a cool drink. This is a hot coffee. Okay, the temperature of this is say like a cool drink is 5 degrees Celsius. That of the coffee it is 50 degrees Celsius. How do it will cool down, and how this cool drink will warm up? Finally, the temperature of this will become 25 degrees. Temperature of coffee will also be 25 degrees Celsius. Now this will become warm drink. Now this will become warm coffee. Temperature of surrounding 25 degrees Celsius. Okay, this is what happens. Now, how did it warm up? Here, it will absorb more heat. And it will radiate less. The rate of absorption will be more than rate of emission. What about the coffee? For the coffee, the rate of emission will be more than the rate of absorption. So here PA greater than P. Here PE greater than PA. How the cold drink will warm up? It will absorb more heat per second than it will emit. It will both emit as well as radiation. So here So what about this? It will be emitting as well as absorbing. Similarly, what is this? Thermal radiation, electromagnetic wave. These are EM waves. What is the thermal radiation? It is nothing but the EM waves, which doesn't require any medium to propagate. So like this, it will warm up, this will cool down. Finally, when at equilibrium, at thermal equilibrium, the rate of absorption will become equal to rate of emission. Similarly, here the rate of emission should become equal to rate of absorption. Both will be equal. Then the temperature of this will not increase nor decrease. So now, so what is the basic idea? All bodies radiate at all temperature, whether it is cooling down. So this will warm up, this will cool down, and this is thermal equilibrium. If a body is warming up or cooling down or a thermal equilibrium, it will be emitting as well as absorbing. So what is the basic necessity condition we'll put? All bodies radiate at all temperatures. So once they attain the temperature of the surrounding, this particular drink as well as coffee, they'll not stop radiating. Still they'll continue. They'll be emitting as well as absorbing. This is one basic necessity condition arises in the thermal radiation. So we should never discuss only emission or absorption. Emission means giving out energy. Radiation means absorbing, absorption means like absorbing energy. The emission, absorption together are called as the radiation. Together are called as radiation. A thermal body will emit as well as absorb the energy at a rate. This phenomena is called as a radiation. Let T be the temperature of the body, M is the mass, specific heat, and there is a thermal body. Temperature of surrounding, let it be T naught. So the body will emit, also will absorb. What is the net power radiated? Which is equal to E power absorbed minus power emitted by power absorbed here. So here we'll assume that T greater than T naught. So the body will emit more power than it absorbs. The net power radiated, we should write here P minus PA. If T less than T naught, then the net power radiated will become equal to PA minus PB. This is a basic equation, we'll write it. Power means energy radiated per unit time. Now we'll compare the radiation of ordinary body and perfect blood body. Before that, first we'll discuss the emissive power. First we'll discuss the emissive power. These are simple, some definitions are there. And these are energy radiated per unit time per unit area. So this will become the energy radiated du by unit time delta T by unit area. Like this we'll define the emissive power. Spectral emissive power means per unit wavelength. What the definition for this will be? Energy radiated per unit area per unit solid angle. This will become E lambda is equal to du by delta delta lambda. This is the spectral emissive power. Absorptive power will define it. absorbed to pure. There's a ratio of energy absorbed to the incident energy. Energy absorbed to the total incident energy. Okay, this is absorb. It's a ratio. It will not have any unit. This will have a unit. Emissive power will have a unit. Absorptive power will not have unit. What is the spectral absorptive power in that particular given wavelength? So next year, spectral absorptive power is equal to energy absorbed over a wavelength by total incident energy over a wavelength. So absorptive power will be energy, total energy absorbed to the total incident energy. If a given body absorbs 50% of the incident energy, then its absorptive power will be 0.5. This is one like this. We define the quantities to discuss the thermal radiation. Kirchhoff's law in perfect black body. Ordinary body will emit and will be absorbing. This is the incident energy. and there will be also reflection. Let me start like this. This is the incident energy. This is a reflected energy. And at the same time, it will be emitting. There is incident power, reflective power, this will be emitted. Is it all the energy incident will be absorbed? No. A part will be absorbed, a part will be reflected. And to be in equilibrium, how much it is absorbed, that much it will emit. Like this will be in equilibrium. What about the perfect black body? Perfect black body, suppose that this is the incident. Then what is the reflection? No reflection. Then for equilibrium, how much it is absorbed, that much it will emit. Here for ordinary bodies, PE will be less than PI. For perfect black body, P equal to PI. How much energy incident, that everything will be absorbed. And for equilibrium, that much it will emit. So who is the perfect absorber? Perfect black body. Who will emit more power? The perfect black body. So what is the Kirchhoff's law? The ratio of the emissive power to absorptive power of ordinary body is equal to emissive power of perfect black body. What is the absorptive power of the perfect black body? 1. What is the absorptive power of ordinary bodies? Will be less than 1 at a given temperature. So who is a good absorber? The perfect black body. Who is a good emitter? The perfect black body. All our discussion will be perfect black body only. Welcome first. This is Stephen's law. The power radiated per unit area by a black body is directly proportional to 4th power of absolute temperature. The total power emitted per unit area directly proportional to 4th power of temperature. To remove this, the proportionality constant T to power of 4. What is T? T is the temperature. What is the surface area? The power radiated. This is equal to directly if this is isolated, then what is it? This power will be dq by dt sigma a t to power of 4, where sigma is Stephen's constant. In exam, they'll give this value. You need to remember. For the dq, we'll have mass, specific heat, ms dt. As it loses heat, negative sign. So the body will cool down. No? So this will become dt t to power of 4 sigma a ms dt. Temperature T naught T0 to T. Like this, you can calculate the time taken for body to cool down. And what is the area of cross section? This will be further. Let me solve it. A very important equation it is. This will become T to power of minus 3 minus 1 by T naught to T. This will be minus sigma. Area of cross section 4 pi r square. Mass will be rho 4 by 3 pi r cube. Minus 4 plus 1 will be 3 here. Then this will become T. This negative sign will not be here. So 1 by T cube T naught cube equal to 4 pi will cancel out. So this will become 9 sigma by rho r. Like this, you can calculate the time taken for the temperature to fall off. It just depends only on the surface area. Now this is about the Stephen's law for perfect black body. For ordinary bodies, it has to be modified. For ordinary bodies, it is modified as E sigma A T to power of 4. What is E? E is called as a emissivity of a surface. For perfect black body, 1. For ordinary bodies, it will be between 0 to 1. This is for ordinary body. So E is the emissivity of a surface. So you take any ordinary body. So what we do is like if this is the ordinary body, this one. Then it will have emissivity E. Okay, agreed? This will be. It will have the emissivity of the surface will be E. For perfect black body, it will be 1. For ordinary body, value will be between 0 and 1. The Stephen's law will be modified for ordinary bodies. Now, if the same body, if it is kept in a box where T is the temperature, then it will emit power and at the same time will be absorbing. So after some time T, its temperature will keep on decrease. So let T naught be the initial temperature. After some time, the temperature of this body will become less than, definitely will become less than this at time T. So what is this body? This will be emitting as well as absorbing. The net power radiated equal to PE minus PE. The power emitted E sigma A T to power of 4 minus power absorbed A sigma A Ts to the power of 4. What is E? E is called as emissivity of surface. The net power radiated will be dq by dt. Like this we can discuss the problem. And for most of the problems, E will become equal to A. They are not equal, we are making them equal. Then dq by dt is equal to E sigma A t to the power of minus 4 ts to the power of 4. dq, what you can write, heat lost minus ms dt. Now you can integrate. Why negative sign? Because with the time the temperature of this body will decrease here. Integrating this will get the required answer. Initial temperature T0, T be the temperature of the body at any time T. Surface area 4 pi r square. It all depends on surface area. This is about the Stephen's law, kept in a surrounding where the temperature is Ts. And we'll assume the temperature of the body greater than temperature of surrounding, so it will start losing out or it will start cooling down. We'll discuss how to calculate the temperature of the sun, the surface temperature of the sun. Temperature of the earth, let it be T. They are separated by a distance x. Here I'll show it. The distance from the sun to the earth. Let it be x. Let the radius of the earth, radius of the sun, let it be RE. Radius of the earth, let it be RE. And the temperature of the earth, let it be T. Temperature of the sun, this one. The sun will radiate, it will emit power in all directions. Of all emitted, only the power which is present, only the radiation which is present in this solid angle will be incident on the earth. Only this radiation will be incident. At the same time, so what will happen to the earth? Earth will be emitting. From Stephen's law, it will be emitting radiation. And at the same time, it will be receiving the radiation emitted by the sun. The sun will be emitting the radiation in all directions. Only the radiation which will fall in this cone will be incident on the earth. No, this is sun which will emit radiation in all the direction. Let Ts be the surface temperature of sun, Re be the radius of the sun, and x is the distance between the sun and the earth, this x, and R is the radius of earth, T is the temperature. The earth will be emitting radiation, at the same time it will be absorbing. Then at equilibrium, the power emitted by the earth should be equal to the power absorbed. What is the power absorbed by the earth? Is it all the radiation emitted by sun will be incident? No, only a fraction. Like a radiation which will lie in this cone only will be incident on the earth. So for this we'll calculate the intensity of sun's radiation at the surface of the earth, equal to power of the sun equal to 4 pi x square. Then the power incident, the sun's power that is incident on the earth, that should be equal to intensity into effective area. What is effective area? 4 pi Re square. So why not 2 pi Re square? From far away, how do the earth will appear for the sun? Will appear like a disk. Example, Chandamama, the moon. If you look at the moon, though it is a spherical, far away, how it will appear like a disk. The same thing with the earth. The effective area will be 4 pi Re square. What we think? No, it will be only pi Re square. So why only disk? Why not surface area, or at least 2 pi Re square? Half of the surface area sun's radiation incident? No, the effective area will be disk here. Then this will be PS 4 pi x square pi RE square. There's a power incident on the earth or the power incident on earth. Then at equilibrium, the power emitted by earth should be equal to power incident. Power emitted by earth from Stephen's law, emissivity of earth, sigma, area of surface area of the earth by temperature of the earth, Te to the power of 4. Power incident, PS 4 pi x square pi RE square. Now this will become E sigma, area of cross section of the earth, 4 pi RE square, Te to the power of 4. Power radiated by the sun from Stephen's law, sigma, area of cross section of sun, Ts to the power of 4 pi RE square by 4 pi x square. Okay, this we have to calculate the temperature of the sun. Ts to the power of 4. Area of cross section of the sun will be 4 pi RS square. RE square will get cancelled out. One more step. E sigma RE square, 4 pi RE square, pi RE square will cancel out. So this will become 4 E sigma Te to the power of 4 sigma 4 pi RS to the power of 4. Pi RE square got eliminated. Four pi x square. 4 pi also get eliminated. Sigma also gets eliminated. 4 E Te to the power of 4. Te this will become 4 will become 2 square and let E be equal to 1. Resultant of this will be 2 x by RS. This will be the temperature of the sun. We know temperature of earth, we know distance from the sun to the earth, I know the radius of sun, I can calculate the surface temperature of sun. A very important formula, try to remember this, this will be more useful for exam. Any good questions can be asked. I will take the next condition. The same Stephen's law application. Suppose say we have the object. Now there is an incident. Radiation. What is the TS? Temperature of surrounding. And T the temperature of the body. There is a surface area. So the power is incident. So according to Stephen's law, so the temperature of this body will keep on increase. T will be greater than Ts. So it will be also absorbing the power from where? From the surrounding. This is the power absorbed. So total power the net power is equal to power emitted minus power absorbed minus P naught. It will absorb the power. Then this will become equal to E sigma A T to power 4. Power absorbed will be A sigma A Ts to the power 4. And there's a power incident. This should be equal to dq by dt. This will be ms dt equal to E sigma A T to power 4 E sigma A Ts to power 4, this P naught. The incident radiation, it will absorb it. Okay, fine. Then it will absorb it from the surrounding and it starts emitting. And if the power emitted is greater than this two, the net power radiated. So in fact, the body, we can write it here, the net power radiated. In fact, it will become negative sign because it's going to lose it. Why? If temperature of the body decreases, it will lose it. If the temperature of body increases, then it will gain it. Like this, we can discuss the Stephen's law with some external power incident and also kept in surroundings. Then following this from the integration, we can work out this one here. I'm just sharing the basic idea. Next, we have the Wien's displacement law. According to this law, what is this? There's an intensity. This will be watt per meter square. Lambda is wavelength. Then the power radiated by a body, according to Stephen's law, we know sigma A T to power 4. The Wien's displacement law will give us relationship between the temperature of the body and the wavelength at which the intensity is maximum. You can say at temperature T3, the wavelength is maximum. So here lambda 3 T3 is equal to lambda M2 T2, lambda M1 T1. T1 is the temperature of body and lambda M1 is the wavelength at which intensity is maximum. And there is a basic idea of the Wien's displacement law, where B is called as Wien's constant. As you increase the temperature, the wavelength will take the lower value. And the area under the curve will give the total power radiated. As you increase the temperature, the total power radiated. So in intensity versus wavelength, so the area under the curve will be proportional to total energy radiated. Area is proportional to total energy radiated. As you increase temperature, the wavelength for which intensity maximum will take the lower values. Like this, we are having the white star, blue star. So red star, you can see the wavelength. For the red star, the wavelength for which intensity maximum will be more. And for the blue star, you can check the red star, the wavelength of the red star somewhere here like this. Blue star will get like this. Then who is having more temperature? The blue star will have the more temperature than the red star. And there's a basic idea about the Wien's displacement law. Then what are the conditions like? Suppose say if there are now for a given body, this is for a lambda T1 equal to lambda T2, lambda 2 less than lambda 1, so T2 greater than T1. Then the power radiated P1 equal to E sigma A T1 to the power of 4, P2 equal to E sigma A T2 power of 4. So T2 greater than T1, so P2 greater than P1. So therefore the area under the curve will indicate the total energy radiated and there's the intensity. So what the Wien's displacement law will give us relationship between the wavelength for which intensity maximum and the temperature of the body. Stephen's law will give us information because of the information power radiated as a function of temperature. Wien's displacement law will give us information about the wavelength for intensity maximum and temperature body. What this given body? A given body will emit radiation of all wavelength. Then the wavelength for which intensity maximum and how it will be related to temperature is given by the Wien's displacement law. There is a difference between Stephen's law and Wien's displacement law. A given body will radiate energy of all wavelength. Then the temperature of the body just depends only on this wavelength. The temperature of the body, it is related to the wavelength for which intensity maximum by Wien's displacement law. It will emit all the wavelength, but there is a one wavelength for which intensity maximum, and that will be related to temperature of body by Wien's displacement law. Hope you are able to understand this concept. Is very, very important. Next we have the temperature. The temperature of this hot coffee is more than that of surrounding. So here it will be emitting radiation. At the same time, it will be also absorbing. Now this will be emission, this will be absorption. So the net emission, the net power emitted will be greater than that will be absorbed. So therefore it will be cooling down. So therefore the power emitted, the net power emitted minus power absorbed. This should be equal to dq by dt. Power emitted E sigma A T to power of 4. Power absorbed, absorptive power sigma A Ts to the power of 4. dq by dt, as the body is cooling down, dq by dt will be ms dt where E equal to A, ms power equal to, we are assuming it. Then if you plot this, we'll get temperature as T naught plus lambda depends on all these quantities. How the temperature will decrease exponentially. Put T equals 0, temperature T naught, after long time put T equal to infinity, the temperature of body will be that of the surrounding. When we solve this mathematically, temperature of surrounding TSR, it is Ts plus T naught minus Ts. The graph will be like this. This is the temperature of body T naught. This is Ts. This is T. The temperature of body will decrease in this way. It will decrease exponentially with the time. Okay, fine. So this is a basic necessity condition. To solve this problem, we'll go for a generalized formula. But every time dealing with exponential will become a big problem. We'll go for a generalized formula. This will be this one only, just modified. This will become final temperature initial temperature minus final temperature by time interval is equal to, this is say some alpha average temperature difference, Ti plus Ts by 2 minus T naught. We can calculate the temperature at any point only for JEE Advanced. Now, those who are preparing for only JEE Mains, you can now skip this topic, not needed. Like this, you can calculate the temperature of the body at any time t. Alpha depends on all these things, mass, specific heat, surface area, emissivity of surface, all these things, the alpha will be dependent. We have there's a source whose temperature is T0. Thermal conducting rod is connected. One end is connected to source, the other end is will radiate like a black body. Emissivity of surface is E. Let A be the area of cross section. Then the wavelength for which intensity maximum is given lambda m. So here, what all the heat transferred by the source, they'll be given to the rod. Rod is here in the form of vibration of atoms and the kinetic energy of electrons. The heat will be transferred. At this particular point, the energy will be transmitted like a EM wave. What is this? This is EM wave. This is nothing but this will become a radiation. Here, what is occurring? A conduction. Then what is H is equal to Ka T naught minus T by L. What is T? The temperature of this surface. We can write in terms of lambda m T equal to B. This H is nothing but the power transferred, dq by dt. This dq by dt again should be equal to power emitted by Stephen's law minus net power absorbed. This will be E sigma A T to power of 4 A sigma A Ts to the power of 4. This dq by dt you can write it as Ka T minus T naught by L. We can find out the unknown things. I'll give lambda m. So from that we'll get the temperature. Solving this we'll get the temperature of the source. So here what all the heat supplied by the source? Here thermal conduction. This end will behave like a black body and it will start converting that heat energy into electromagnetic wave and it propagate. From Stephen's law, the surrounding, due to surrounding air also there will be temperature. Temperature of surrounding is how much Ts. So then this end will emit and also will absorb. So this will be PE, this is PA. What about this H? What all the power transferred by the rod? That is equivalent to this resultant of these two. Okay, agreed? This conduction radiation like this you have to remember. This will be very, very important. The body will emit and also will radiate. One more condition, there is ideal gas. There is a thermal cubical metal vessel. The outer surface will have emissivity E. It will also will be emitting. And this will be very useful for you. Sir, what are red color arrows? Red color arrows are thermal conduction. What about the curved arrows? Black color. They are the emission. At the same time, it will be also absorbing. Okay, fine. So this is the absorption. And this will be the thermal conduction. So what is happening here? Thermal conduction will occur, emission will occur, and absorption will also occur. Now the net power transferred will be equal to power transferred due to conduction. I'll write like this. Power transfer due to emission, then absorption. This should become equal to dq by dt. Power transfer due to conduction. This will become Ka T naught minus Ts by D. 6 surfaces already I discussed. Power emitted, only outer surface is responsible for emission of power. E 6 faces, E sigma 6a T power of 4. Power absorption A sigma 6a Ts to the power of 4. It will lose it, so this will be NCV dt. There's a general equation you should learn to write. Rest everything we can manage. For all our discussions, we can write here. What is this? Power transferred due to thermal conduction. Power emitted due to Stephen's law. Power absorbed due to Stephen's law. The surrounding air also, from there also the energy will be incident, that will be absorbed. The net power will be transferred. NCV dt, it will decrease, so negative sun. Why negative sun? The temperature will decrease with the time. Both conduction as well as radiation is what I included, and even thermodynamics. So what is this entire problem? You're having conduction, radiation plus thermodynamics. These are ideas you should have. Rest all mathematics, solving this and moving forward. This is a general approach. Radiation, thermal radiation. Try to understand thermal conduction, what it is. Whenever you see any surface heat passing through it, thermal conduction. Whenever any object is there having temperature, it will emit. And if any surroundings is there, through that also it will absorb heat. Next we have the convection. We know this will be, from here is what we are supplying the heat. The heat supplied by that here will be absorbed by the molecules. As we absorb, so here we can call 1 and 2. What actually happens? The temperature T1 will be greater than T2. Because of this, as temperature increases, the density will decrease. Rho 1 will become rho 2. The lower density one has to move up. So the molecules here starts rising up. Then when they are moving up, these molecules, they'll have heat and they will transfer to the adjacent molecules. Like that, they will lose heat. So what about here? The medium is involved in the transfer of heat, and also the medium itself will propagate here. This is what happens in the case of thermal convection. Agree this? So like this, say convection current is set up. So the hot water will rise up, will reach onto the surface. Once it loses the temperature, density decreases and will fall back. Like this, a convection current is set up. Warm molecules will rise up, the cool molecules will slide down. In this way, there will be a convection current will be set up here. This power transferred by the convection current, we have a small general form. In the convection depends on coefficient of convection, which will have unit watt per meter square. This is the power transfer or power flowing. Area of cross section and the temperature difference. So here in the convection, both the heat and the material are involved in the transfer. Medium and the energy both will flow. In case of thermal conduction, only the energy will flow, medium and rest. In case of radiation, no medium, only energy will flow. There's a basic difference. Conduction. In conduction, what happens here? Medium will not flow. Energy will flow. In place of convection, medium will flow. Energy will flow. In case of radiation, no medium. And energy flows on its own. Okay, these are basic conditions. Okay, kids, we had a discussion about the thermal properties of matter in one shot. We have discussed, first we started with the thermal expansion of solids. In that all the ideas I explained. Quotient of linear area, volume expansion, then expansion of the disk with hole, sphere with cavity, time loss, time gain in simple pendulum, thermal expansion of rotating disk, thermal expansion of rods with spring, thermal expansion of scales, thermal stress, thermal strain, and some other application problems. Small ideas are there, formulas are very less, and variation of density with temperature. These things we had the expansion of solid, expansion of liquids. Very small concept. Apparent expansion of liquid with respect to solid equal to expansion of liquid minus expansion of solid. This is the one formula. Then apparent expansion equal to mass expelled by mass remaining into change in temperature. Two formulas are there. Specific heat Q equal to ms delta T and heat capacity equal to ms watt equivalent of calorimeter mass into specific heat of calorimeter. Then latent heat of fusions we define, and some if ice added to water, ice added to steam, some related problems. You have to go through it. Very simple and very important. Among thermal expansion of liquid solids, calorimeter very important for example. Next, thermal conduction. This most things like current density, series, parallel, thermal resistance. You revise this, you are revising current density. Some part like a thermal resistance, series, parallel. All the formulas will be same. There R equal to rho L by A, here R equal to L by K. The formulas, ideas will be same. Almost the initial part of the current density and this will be same. So you have to compulsory revise this. It will help you in current density. Then some rod connected across hot and cold bodies. This only the difference, remaining all are similar. Then thermal radiation. Here some formulas are there, Stefan's law. Only I think the formulas will start from Stefan's law, Newton's laws of cooling, convection and Wales displacement law. These are related to some 4 or 5 formulas are there. So in all this, you come across the formulas. Remember the formulas first. Understand the concept, remember formulas, solve PYQ. You can see the benefit in exam. This is a method. You can't just watch and go. Because you watch. If you don't know formula, what you do in exam, not possible. Please come out of this one. Most of the students, what they think is like a sir will teach in such a way that you watch, you'll get a rank. Not possible. You have to watch, understand, remember formulas, solve PYQ, go to the exam, you'll get a rank. I am only 5% here to help you. 95% you have to help yourself. Please. So it's very important. Now another 10 days April session exam is there. Open your eyes, start reading how much of possible. You have an exam on April 2. Till April 1 you read it, no problem. Reading is important for exam. So till last date you keep on read and revise. Nothing will happen. No need to stop anything. Keep on read. You have technology, just open the YouTube and start put into 2 times and just scroll the video. Keep on scroll it. The more you see it, the more you remember it. This is a basic thing. Fine. Okay, thank you everyone for great support. I'll upload the next the modern physics one. Thank you everyone. I'll end up the session.